global illumination techniques that go beyond the standard rendering equation. We're going to consider ray tracing, radiosity, and ray marching, and some of the other ray path algorithms. So far in this class, we've been looking at local illumination. And local illumination is the basis of the standard shading equation we've done with diffuse, specular, and ambient terms. It's something that can be computed quickly. It's something that gives us accurate enough results for making scenes look real enough for interaction, but it doesn't give us enough to make scenes that are truly photorealistic. So here's an example of a scene. We have a light, we have an eye or camera, and we have the vertex. And the light rays, we're considering basically direct light rays that come down to the surface and bounce in a specular direction directly to the camera, or which take a kind of diffuse approach and then bounce in all sorts of directions, and then some of them reach the eye. So we're basically considering the direct illumination of a surface with light. Now, one of the characteristics here is that we consider each triangle separately, so even if there is a shape in the way, like right here, we consider direct illumination on that shape, but then we ignore it when we do direct illumination on this shape. And that's what we've been doing. We're going to look at methods which consider global illumination. And so we'll go to global illumination, and we'll consider methods which account for indirect rays. So the light source here generates light rays going in all directions, which bounce off the walls, maybe multiple times, and then illuminate it. So you know, if you shine a flashlight on a wall, the rest of the room will still be illuminated, even though the room is not under direct illumination from the light source. So we're going to account for indirect rays. The more indirect rays you account for, the more realistic your rendering is going to be. The problem is that the more light rays you account for, the more expensive it is in terms of computing time. So we're going to look at methods that vary in the number and the nature of the extra light rays that they consider. So far, this is just to repeat on the local illumination. What I've said is that we're looking at local illumination, direct rays, the diffuse and specular rays, and we're basically taking the light into the image. So we're going out to the scene and rendering each triangle and asking what light goes off of it into the scene. We're dealing generally with opaque surfaces, so we're not looking at translucent or transparent surfaces. There's no shadows or crosstalks between the facets. So this picture, you'll see that there is apparently a light coming from this direction, but there's no shadows being cast. We would expect a shadow to be cast here. We might expect a shadow to be cast down here by the sphere. But in this case, each of the little facets is being rendered independent of all the others using our shading equation, and that's giving us a scene which is realistic enough for some purposes, but not enough to be truly photorealistic. If we go to global illumination, we're going to consider many rays, direct and indirect, as they bounce around the scene. We're going to be more scene-oriented in that we're going to consider all triangles and lights at the same time. So instead of considering, as we do now, using a standard shading equation in our algorithm, one light and one vertex, compute the shading equation, get another vertex, compute the shading equation, get another vertex, compute, and get the shading equation and compute it. Right now, we're doing every vertex and every light and doing the computations separately. Now we're going to put it all together and compute solutions that involve all triangles and lights simultaneously. We're going to be more image-oriented. We're going to go to the image and ask, what can you see in the image? What objects can a pixel see? We're going to get new effects, translucent, transparent surfaces, refraction as it goes through a light like this, a sphere like this sphere here. We'll consider shadows and color bleeding. So we'll get shadows, and that's called acoustic, which is an interesting effect as light goes through the sphere and focuses. So we're going to look at all sorts of new kinds of lighting effects that we can get when we consider a more complex scene and do global illumination. Ray tracing and radiosity are the two techniques we'll take a look at today, and we'll look at more later. So we'll look at the general concepts, what's behind them, what advantages do each of them have, how can you spot a ray traced or radiosity image. We'll do an overview of how each works, and then once we get this is going to be one day, and then next day we'll keep going on with more advanced techniques for path tracing and ray marching that will enable us to work with more surfaces and work more efficiently. So here's an example of a ray traced image. Very common to see an image which has spheres and planes, surfaces that are easy to compute with for ray tracing, and you'll end up with reflections, and so things reflected in one another, refractions as light goes through glass or other kinds of translucent and transparent medium. You'll get sharper shadows. Then some other methods. So there's a sharp shadow there, a sharp shadow there. It's a partial physical model. We're not going to be completely physically accurate in terms of light transport throughout the room. We're trying to model light transport in a space and how light goes from surface to surface. And ray tracing accounts for more rays than our direct illumination model, but not all of them. We'll generally deal with point lights, and we'll trace single rays, which is one of the reasons why we get sharp shadows, because we're going to trace a single ray as it bounces around the scene. It can give a very, very sharp and very, sharp is the word I started with. It's just a well-focused scene, and actually you have to work in ray tracing to get things out of focus. That takes some extra work. So it looks at hyper-realistic, hyper-focused images. Radiosity is a different method that accounts for global illumination. When you see radiosity, you're more likely to see soft shadows. So we have, shadows here that are very soft, because radiosity is accounting for more paths, and more paths means you get more paths around an object, and therefore the shadow is a little bit softer. Better physics involved. You can do extended lights, so you can have lights that aren't just simply one point source, but could be a large fluorescent light or some such object. So you can basically have extended lights more easily. Like this window is effectively an extended light. This is an extended light up here in this image. You end up with very realistic scenes. They're often radiosity is very good for architectural scenes, because buildings can have specular elements, mirrors or glass or stuff for accent, but generally we want diffuse spaces to live in, because it's a more natural place to move around. You wouldn't want a completely mirrored room. It'd be hard to navigate. Just imagine an apartment which was completely mirrors, and trying to walk around that day after day. So radiosity is often good for architectural modeling, because it models human space as well. All right, well, we'll go over the basics of radiosity and ray tracing in the next couple of videos. Ray tracing is one of the first and most remarkable global illumination techniques. It's been around quite a while, and it gives results which are very clear and sharply focused, and impressive. So to understand ray tracing, you understand a few principles. One of the principles is that we are going to cast rays through the image. So we're going to start here in the camera. We're going to pick a particular pixel, and we're going to take the focus point of the camera, and we're going to send out a view ray into the image into the scene and ask what the view ray intersects. We're going to do one view ray for every pixel. So every pixel is going to get its own view ray. So essentially, inverting the usual way we think of taking a picture. Usually we think of light coming from the scene and then into the image focused through a lens. What we're going to do is, in this case, is the reverse. We're going to take this camera, which we should think of here as a point. We're going to cast rays through the image and then ask, what does this pixel see? So we're asking what a pixel sees. So at the first level of ray tracing, we send out our view ray. It hits this sphere, it picks up this color, and this color ends up being put in the image. If we send out a different ray, and the ray goes out and doesn't get anything, then we end up putting no color in the image. So that's the first step. But the trick is that we're going to have, we're going to continue our rays. So we hit this location on the surface. We're going to cast additional rays. One of them is going to be ray towards the light source, asking what's the contribution of the light to this particular point. This one's going to be similar. If we go through a surface, okay, let's say we hit this bottom, where we have a shadow, we're going to cast ourselves up towards the light, but we'll notice we'll intersect someone else, and therefore we have another object here, a shadow. So we'll cast shadow rays to figure out if we can see the light source and if they're illuminated. So that's a first stage of ray tracing. We cast a view ray out, hit a surface, and then cast ourselves the light source and determine whether shadow. Now, there's a number one. It depends on having all the other objects in the scene, because when we're hit down here on this plane, we need to go through all the other objects in the scene and see if our shadow ray intersects with the light source. So number one, we're already considering other objects and surfaces in the scene. We're going to send out the view or primary ray, and that's going to go from the image to the surface. But then we're going to send out secondary rays. And secondary rays are going to be shadow ray to all the lights, reflection ray, and a refraction ray. So this is the arrangement of all the rays that we need to consider for the moment. We're going to start at the camera. So this is the camera focal point. I don't know why I'm getting the extra marks. And we'll send out the primary ray. Primary ray goes out into the scene and hits an object, or doesn't. Then we determine, from this point, what is the contribution of this point to the final image? Well, the first thing we do is cast out a shadow ray and see if we're illuminated by a light source. If we're diffuse, that might be enough. But if we're specular, we might send out a reflective ray and see where that reflective ray hits. If we are refractive material, like a transparent glass ball or water or something else like that, we might send out a refraction ray. And so we're going to cast a ray out, and we're going to send secondary rays out to figure out what sort of objects or lights are illuminating the surface spot that we're at. And we're considering the entire scene when we send these out. Now, the key thing to ray tracing is that this could be recursive. So a ray tracer is a simple recursive program. It's not very efficient when it's simple, but what we could do here is send out a primary ray. Primary ray goes down here, and then it hits this ball. Then it goes up and hits this object. And let's say this object is, again, like a mirror ball. It's reflective. Then we'll send out another ray from there. And we'll send out a shadow ray from there. Essentially, we'll be sending out rays. And then if there's another object up here, we might send a ray out from this. So we will trace rays through the scene until they dissipate, because every time you hit a surface, you lose a certain percentage based on the reflectivity of the object. So we'll wait until the ray becomes inefficient. It no longer carrying much light, or we run out of time because we only want to send rays so far. So we're going to basically, it's going to be a recursive casting of rays. Now, here's a slide which basically emphasizes that recursive element that we're going to send out. The primary ray hit this large white object, and then we're sending out the shadow and reflective ray from that. And this object is not, blue object is not refractive, so we're not sending out a refractive ray. So here's some of the things we add. So previously we had the diffuse, specular, and ambient components. Well, we're trying to replace the ambient components. So we have diffuse and specular components. So the diffuse is going to be managed largely by the light ray. The specular is going to be handled a bit by the reflection ray. And then we're going to have refraction rays. And refraction is going to be based on an equation we haven't done yet, which is going to be essentially the ratio of the speed of light between the two materials. So if we have water and glass and air here, so we actually have three materials here, you can see that the water has a strong refractive index relative to the air, and we end up being able to see the straws greatly enlarged and displaced from their what is apparently the path going down. So there'll be an equation which is like our reflection equations based on the angle and the ratio between the two mediums. And so you get these kinds of images where you have a great deal of this is a good example here of a refractive image, the one here on the bottom. So this one right here, you can see that there's a target in the back being refracted through the glass sphere, which is an effect we don't get through our original one. And this glass is refracting the back wall. This one involves, I think I may have put a couple images in this one. I'm not sure how much these are refracting, but you can see in these cases reflection, that the reflection vectors are giving rise to very good specular objects, not just with the highlight, but with reflection of the background and other surfaces in the scene. So here's, when we take a look for a traced image, you can see here, this is our standard Phong blend style shading that we've been doing, and you can see that we're rendering things that looks reasonably accurate for being able to interact with it. If you find the game, the highlight here on the teapot obviously is there, but in this case, in the bottom, ray traced, we get reflection of the scene in the teapot, not just of the light. We get different effects, like the spoon here gives a kind of focusing on the bottom of the teapot. We get a bit more reality to the shadows, other things going on with the saucer, just a little bit more realistic. So if you see something that looks hyper realistic, like this car, very specular, very hyper realistic, that's probably ray tracing. Now, tweaking ray tracing, one ray is not enough, because if we have a pixel here in our image, and we have some object in the scene, we send one ray out, we might hit there. We send another ray out, we might hit there. So what we generally do now is we do stochastic or random ray tracing. So we may send out lots of rays from one pixel. It will sample what it sees and compute that. And so this pixel will be an average of everything. So most ray tracers now are stochastic. They send multiple primary rays out, and they may make random decisions on when they do and do not spawn secondary rays. And then we want to speed this thing up by having a data structure which gives us more efficient intersection with the scene. If you don't want to have to test if your ray intersects with every object, because then you have 1,000 objects in the scene, you have to do 1,000 intersections. But we know we don't have to intersect anything that's behind one object, or we don't have to intersect something that's up at the top when our ray is being cast towards the bottom. So we're going to use some sort of spatial data structure to speed things up. And then there's variations on this, on how we do ray tracing, which give to all sorts of path-based algorithms where we trace light from the image to the scene, from the light to the scene, and we consider as many paths as we can in an efficient way to get a more accurate image. Radiosity is a global illumination technique which is more physically accurate than ray tracing, and certainly than direct illumination techniques. It's very expensive, very hard to do in real time. It involves essentially the work of computing the light transport through all surfaces of the scene accurately, as accurately as you can do in equations. So one way to think of ray tracing, and we'll talk for a second about referring to this particular slide. What happens when you fill, you dump a bunch of water into a cup? You just dump a bunch of water all of a sudden. It splashes around, goes up and has these waves and such until it finally settles down to a flat surface in the cup. So if you think about radiosity, the scene, it's basically you all of a sudden illuminate the scene, all of a sudden you turn on all the lights, and all the light rays start bouncing around faster than we can perceive because it's the speed of light. But sooner or later, all the light paths kind of balance off. So you start on light, and the light bounces off the top of the scene, it bounces back to the bottom of the scene, bounces back, and keeps bouncing back, and sooner or later it reaches an equilibrium. So radiosity, what we're going to try to do is compute the equilibrium of all the light in the scene as it bounces around. So down at the bottom, we have the two examples of direct illumination. And so that's where you have, this basically illuminating each object directly from the windows. But in radiosity, we're computing a more global solution where we're accounting for more light paths, and therefore we're getting things which are a little bit softer shadows. We're accounting for bleed. So light comes in here, hits the back of this, and bleeds onto the wall. So the wall is a little bit there. You might get bleeding, in this particular case I can't see it, of the red carpet onto the red floor onto the surfaces. So we have a little bit of red here at the bottom, at the top rather, where we're getting bleed from the floor onto the ceiling. So basically what we're doing is we're trying to figure out how the rays bounce around the scene off of each surface to another. So this is an example here with the chairs, a ray traced image of a radiosity image, where we get some nice effects and some complexity. It's a lot going on in the image. This one feels a little bit like it's ray traced. By the way, this window in the scene outside is probably, I don't know the origin of this one exactly, a flat image on the back. It's an environment now. So it's a picture that's supposed to look like the background. So it's a little bit of a texture map there to get that background. The Cornell box, University of Cornell, is a famous way that this method was developed. We're trying to take a box with a light source at the top, so like this, and make an image that's artificial, that's indistinguishable from a real image. And by having such a simple environment, a box with one light source on top, they can control it so that they can have an experiment that's very controlled between the perception of a real box with real objects and a fake box with a synthetic image. So you can see here a bunch of radiosity effects. You can see that the teapot has a lot of color bleed. So we have color bleed here because we're going to get red on this side from this wall and green from the other side. We're going to get some soft shadows because it's a hard shadow when they're around the edges too hot, but the light is bleeding off of the wall and lots of radiation and softens the edge of the shadows. So you can see here that we have this ad. So the Cornell boxes becomes the vodka ad. The Cornell box requires radiosity. So we're basically seeing the little square light at the top, extended light. So it's not just the 29 Chester spotlight, light direction, it's an extended light. And then you have various lights, various walls. Notice we have specular and translucent and reflective effects in here, which we can manage in radiosity. We can also combine ray tracing and radiosity and get to a hybrid effect. So here is an example of how radiosity works. So, as opposed to ray tracing, we sample rays for each light, reflection, refraction. So we're going to sample instead of rays. Look at the radiosity, and the key element is we're going to integrate over all rays in a patch. So we're going to have two patches in our scene, a patch here on the wall, and say a patch here on the ceiling. And there's a bunch of light rays going back and forth between them, like this. What we're going to do is integrate over all rays between those two patches. So count for every ray in some sense that goes through these patches. It's a large interval because we're integrating over a number of directions, but it can be specified. And we're going to basically use some finite elements time. And so we're going to have a whole bunch of patches. We patch the entire scene, and then compute the light transport between each patch. That's a slow iterative process. So we're going to essentially start with a dark room, and then we'll turn on the light. You kind of see this kind of directly illuminated. So the first stage, that's the first bounce of all the lights. And then we add more and more. The room gets lighter and lighter, and we'll start to get some different effects and possibly some color information going from surface to surface as we account for more and more bounces. We basically iterate our solution until it becomes stable. It's like the tub and the water splashing around. Here's an example of patch computations. On the right, we have the Cornell box grew into a whole bunch of little patches, little triangles, and essentially we're going to set up a huge matrix, and the matrix is going to account for every one of these patches, every one of the other patches. So that patch to that patch, that patch to that patch. And so you can see that we're going to get a big matrix. Okay, there's going to be thousands of patches. And so we have a 1,000 by 1,000 matrix. Some of the terms will be close to zero from shadowed from one of the patch to one big object. I may not have a contribution, and the corresponding element of the matrix is zero. Essentially, we're going to evolve this matrix until we're accounting for all of the light going back and forth between the surfaces accurately. And so the result is what I've shown you a little bit before. Very good for interiors. You can account for perspective and other kinds of effects there. But it just gives a very soft, typically very soft and very accurate image, something that's very good, as I said before, for interiors. Interiors are slightly controllable because you have walls, and walls have planar surfaces, and you get your equation slightly under control. If you start to radiosity a forest with a bunch of leaves, you've got issues. So at this point now, I hope you can start to identify what an image may have, the kind of global illumination effects that come with radiosity, soft shadows, extended light sources, and kind of a soft buttery look in some cases. In this video, we're going to start the details of ray tracing. We're going to go over basic algorithm. In later lectures, we'll go over different approaches to ray tracing to make it more efficient. This is the simple and straightforward approach. So we're going to go over the basic recursive algorithm, how to cast the primary ray intersecting with an object, and then we'll go over computing the refraction ray and the other issues with respect to reflection and refraction. The reason why I mentioned only the refraction ray is because the shadow ray is straightforward because you're at a vertex and you simply cast a vector to the light by doing the difference of the 2 points. That's straightforward. And if you're doing a reflection ray, we've already done that. So that's why I focus here on the refraction ray. So here's a basic ray tracing algorithm. We have 2 parts to this. The first part is initial nested loops that go through every pixel in the image. So we're just going to iterate over every pixel in the image and cast a ray from that pixel into our scene. The casting will be done by the recursive ray trace algorithm. So we'll cast a ray. And this array is basically a data type, which is array is a point plus vector that enables us to compute intersections and other things that we need. They start off with 0 for the first generation. When we go to a max number of generations, we'll quit. So when we look at the code, if we go over the max gen, we quit. And that's we just return the background color because we hit no objects. We're just going to assume that we're not going to do any more intersections with objects. Next thing we do is we figure out the intersection of the ray with the first object in the object list. So if we've got a lot of objects in our scene, 1, 2, 3, 4, 5, right, and we cast a ray, we're going to figure out the hit point being the first object we hit and not any other objects we might hit through the scene. So we're going to find that point right there. So the return here is a hit point is going to be a point in the scene. If the hit point is equal to null, meaning we didn't hit anything, we return the background color. So if we just go through the scene onto infinity, we're just going to give whatever sky color, blue for a sky or something else that gives us a background. Then once we have this hit point, for every light in the scene, we will compute using the standard shading equation, the diffuse component of how that light directly hits that surface, and it goes back to the camera. If there's a shadow ray, if the light, if the ray we cast goes through another object, then we accumulate nothing for that light. So that accounts for shadowing. Then the next thing we're going to do is do the reflection ray. So the reflection ray, if the hit point is reflective, meaning it's got a reflective component to it, we're going to compute the reflection ray at the hit point. So this is going to be for that point on the surface. We're going to compute the hit point, and then we're going to recursively call ourselves on that ray. So in this case, the operation of this is recursive. We hit the hit point, and we're going to then go off and recurse and find another surface to hit, and then do the computations at that surface. And we'll accumulate some color, treating that as if it's a light. And then we will do the refractive ray, where we assume that the ray goes through the object, refracts through the object, and see what it hits. So then we'll do that in a similar way to the reflection ray. So this way we'll spawn secondary rays throughout the scene. The shadow ray is not recursive. We just simply go from hit point to the light. The reflect and refract rays are recursive, and we go off and see what we hit and bring the color back from there to our computations. Casting the first ray is essentially what we've done in class before. We've given P0 and P1, we made a ray based on, we would call this P0, we would call this P1, and so we basically have, our standard equation that PT is equal to P0 plus T times V. So that's the equation we've worked out before in class. We're going to basically put the I at the origin for this simple case, and we'll have some distance D, and then we'll have some height Y, and then each of these little separations will represent a new pixel, and we'll cast rays for each one of these pixels out in the scene and see what we hit. We set this up in terms of the focal length D and the height Y prime in terms of what we want to see in the scene. So as we manipulate those, we'll magnify or shrink the scene. Okay, intersecting with the first object, we've got an object list. We're going to go through the object list one at a time and see which one we hit. We can use a smart algorithm and a smart data structure to speed this up. For the moment, we're just assuming we're going through a linked list and hitting the first object, doing intersection for each object. And we'll find the hit time T when the ray hits the closest object, so the smallest T. One thing to be clear about is sometimes we're using the term T, but we really mean like distance into the scene. So hit time and hit distance, it depends on how you compute it and what it's proportional to. Right now we're going to be doing hit distance. So let's look at how you do a sphere in a basic case. Okay, so I'm going to have a ray here that's cast off in the scene. And so I'm at my P0, my original point. I have V, which is my vector, right? And my ray here essentially is going to be P0 plus T times V. Okay. Now, if we have magnitude of V equal to 1, then T is effectively distance. So there's advantages to normalizing the vector V. Now we put a circle here. Now in 2D it's a circle, it's a sphere in 3D. And we have a center, so CX, CY, we'll call that the point C. And we have a radius R. We want to ask if the distance from the point to the line here in a perpendicular direction, I don't know why I'm getting some of these spurious lines, that we want to see if this distance D, D is less than R, hit. If D is greater than R, we have a miss. What happens if D is equal to R? Okay. What happens if we, what computations should we be doing if we have D equal to R exactly? I'll let you think about that. So let's do the computation here. What we're going to do is do a projection. This is in the dot product handout, which we just had before the midterm. So I'm going to do the computation this way. I'm going to compute a ray here to the a line segment or a vector. I'm going to compute a vector. Let's call this vector. I don't think that yellow is the best color, so I'll use this one. So let's call this U, right? So that's U. And we want to decompose U into two perpendicular subvectors. We want U equal to U1 plus U2, where U1 is the vector that goes here, and then U2 is the vector that goes here. Okay. And then the magnitude of U2 is going to be equal to D. And so we'll use it, we'll project, I'll switch back to red here, project U onto V, and let's for the moment assume that projecting, so we'll set U1 equal to U dot V over E dot V times v. Now, quick computation, this is equal to, I have to update my driver, u dot u over magnitude of u squared, v squared times v, which is equal to times u over magnitude of v, I'm sorry, I keep saying u, but I mean v, magnitude of v, times v over the magnitude of v, which is u dot v normalized dot times v. So we're going to new vector, which is really the length of the projection of u onto v times v, and if v is normalized, you notice we don't have to do any of that pesky division. Now, since we have u equals u1 plus u2, then u2 is equal to u minus u1, so which is equal to u minus u dot. Okay, so this is the way to do distance from ray to sphere in our vector geometry. There's another approach which works with plugging the ray equation into the implicit equation for the sphere, and we'll do that next time. So now, once we've hit the sphere or object, now we have to compute the reflection and refraction rays, and this pretty image is just to remind us why we're doing this work, because we want to be able to have pretty pictures like this. So we'll get the mountain reflected into the lake or the straw refracted through the water. So just to make sure it's clear, so we'll hit this point. All right, we'll have to have the normal, and we have the hit point, which is location. So we're going to have two pieces of data, the hit point, and then we'll have the material for that, because we'll want to know the material at this point. So we're in a position here to do the computation of the standard shading equation, and if we simply want to do direct elimination, we'd simply figure out the rays to every light source. Okay, that's a light source, and we do the shadow ray, and I'll do that in a dark blue in case, to the light source. It's called a shadow ray, although if we hit the light, we get the light illumination. So at this point, we have got the standard way to compute diffuse illumination, and that's what we accumulate. But now we're going to compute the extra rays. We're going to compute the reflection ray, and we're going to compute the refraction ray and see how they go. Okay, that's the end of this video. Oh, not quite. There are some newer algorithms which we'll go over where we have variations on ray tracing that try to multi-sample and randomize the way we go through paths in the scene. We may start at a light and take paths from there, or take paths from the camera. So there's a number of algorithms that fit into the path strategy. And ray marching is a version of it which uses binary search to find the hit point for complex shapes when we don't have closed forms like we do with a sphere. So if we want to do some complex shape, we may have to use a ray marching approach. All right, so we'll look at some of those later on. Okay, this video is going to be on Snell's law and refraction rate. So I know, pretty picture again, just to show it off again. Refraction is going to be the one on the right. We're trying to figure out where rays go to a change in medium. So when we go from air to water, or air to glass, or air to diamonds, or air to any kind of medium, it's different. We end up with refraction. And one effect of refraction is to the viewer, the object appears to be in a different position. Basically, we need refraction to be transparent surfaces. Even if we have a pane of glass, it's fairly thin, we may not get much refraction. When we look into a window, we don't expect things to be drastically different like the straw, but we'll need the refraction equation simply to do the computation from the transparent object. Okay, so the key here is that the speed of light depends on the medium. When we go from air to water, the light will slow down. The speed of light is defined in a vacuum. Vacuum is our standard. So when we go to from one medium to another, there will be a difference ratio. Now, the metaphor here is if you are trying to reach a point along a sandy beach. So we've got a beach here, and we have a sidewalk. That's not a very good color for that. Maybe that in blue. You've got a sidewalk, and you want to reach to this point in the water. So, if you ran straight, you're running through a lot of sand. The sand is slower to run on. The sidewalk is faster to run on. If you ran this way and then had 90 degrees, it would be slower because you would have run farther on the sidewalk than you needed to. You maximize the fast sidewalk versus the sand, but you're still not optimal solution. So the optimal solution is to go to some point where we basically have the ratio of speed on the sidewalk and the slower sand gives us an optimal ratio. And so we run as far as we can, and then we determine that we can then jump to the sand and run. So refraction is essentially if you think of light trying to take the shortest path to our eye, it computes the shortest path through the refractive medium. And I'm going to go so far in the fast medium and then go through the slower medium for a shorter distance. So this metaphor of running on a beach is kind of a metaphor for the shortest path approximation that light is using. All right, so I messed this up, but let's do this. Let's clear some of the stuff here. So here's some indices of refraction where vacuum is equal to 0. So vacuum is equal to 1 rather, 1.00. And so these are ratios. Diamond is around 1.5. So the index of refraction is basically going to be the speed of light in near medium divided by the speed of light in the vacuum. Change in phase velocity leads to bending of brightness. So we're going to go over Snell's law. And we'll go over the law and we'll do some examples. So essentially, Snell's law is saying that the ratio of the sine of the angles is equal to the ratio of the refractive indices. So n1 and n2 are refractive indices here. So n1 and theta 1 are this ray that comes into this vertex point here, and with a normal vector. And we hit this point, the angle between our ray and normal vector is theta 1, and we leave in this particular case in the slower medium, theta 2 is going to be smaller, and so our output vector is going to be p. So we come in with p, and we leave with q. This is good for 2 dimensions. When we go 2 dimensions, we're going to have a slightly more complex equation. So the vector form in 3D, and there's an issue here, and I'll show you the vector where we're going to basically compute the refractive vector using this times your b vector, and that's v, and that is r, and this is n. So relabeling our different vectors in the diagram, we're basically from v and n into r, which is very much like what we're doing in reflection vectors. Okay. Now let's look at how these equations work in a little bit more detail. So the basic equation we have is that, we draw our diagram. We have v coming in, and we have r going out, and we have the normal n, and we have theta 1. That's particularly bad. We have theta 1, and we have theta 2. Okay. And we know this, we have n1 sine theta is equal to n2 sine theta 2, right? So that's essentially equivalent to our ratio. Now first let's look at some implications of this. If we have n1 equals n2, what does that mean? Well, it means that the signs are going to be equal, and therefore the angles are going to be equal. That implies theta 1 equals theta 2, which implies that our ray goes just straight through. So our input ray V and our output ray R are essentially the same vector. Well, let's do another case. We're going to do n1 equals 1, which is approximately air, and n2 equals 1.5, which is approximately diamond. And let's set theta 1 equal to 45 degrees. So we're coming in at 45 degrees. And how do we leave? Right? So we can set up this equation. Right? So if n1 sine theta 1, so what we want to solve for is theta 2. And we do that, we get theta 2 is equal to inverse sine of n1 over n2 times sine theta 1. Okay. And just throwing the numbers in for exercise. Okay. Ratio to refractive indexes times the sine of the first angle. 1 over 1.5 times sine 45 degrees. Okay. And that's equal to sine inverse approximately 0.07 divided by 1.5. Okay, I'll approximate it here, which is approximately equal to sine inverse 1.5, which is 30 degrees. So this is going to come out at 30 degrees. So it's going to slow down the diamond. Now, if we do another example, and to do another example where we have like the ratio of water, air, or something smaller. If we just look at this, we can see that we have N2 is greater than N1, so we're going into a slower medium. And in our original equation here, if N2 is larger and N1 is smaller, that means by the ratio, then sine theta 2 has to be smaller, so the angle has to be smaller. So this implies that theta 2 is smaller than theta 1, so we come in and we go sharper, we bend in. If N2 is less than N1, this implies the opposite, theta 2 is greater than theta 1, then we come in and we go faster on the bend away. So that's some of the intuition behind Snell's law. Let's do one more case. We're going to reverse our previous case. We're going to have n1 equal 1.5 into equal 1, and we still have theta equal to 45 degrees, theta 1. And then we have theta 2 is equal to inverse sine of n1 divided by n2 times sine theta 1, which is equal to sine inverse 1 1.5 over 1 times 0.707. This is equal to inverse sine of 1.06. Well, inverse sine only works if values are between -1 and 1, so there is no solution. This is generally the case when we come in at an angle and our output angle would be greater than 90 degrees. So essentially, we are, if you notice with this particular case, our N1 is greater than N2, so we're going from a slower material to a faster material, so our angle will tend to be up from this. In this case, it's so extreme that it goes along the boundary between the medium, and this is a case we'll get to on the next slide. So total internal reflection is when we end up with the light not going through the surface, bending back in and reflecting back in, so into the surface. So this is the case of a turtle in the water, and the turtle's being reflected like a mirror into the water. The light is being trapped in the water and not going through the water at this particular angle. So we have a critical angle, and that is when we have theta c equal to n1 over n2 over n1. That happens when we get theta 2 equal to pi over 2. If you remember the angles, this is theta 2, theta 1 is the difference here, theta 2 is the difference here, and if theta 2 is equal to 90 degrees, then we come in and we're going to leave right along the boundary. So that's the critical angle when we end up with theta 2. We can compute that because we set theta 2 equal to pi over 2. Sine of pi over 2 is equal to 1. And so when we punch it into our equations, we can end up with a critical angle. Another way to look at it here is that if we put this in this, we're going to end up with theta 2 is equal to arc sine n2 over n1 times n1 over n2, which is arc sine of 1, which is 90 degrees. So going forward, you see that we can figure this out. To spend a minute on it one more time. So if we have we're coming in, and then so we're at theta 1, but we assume theta 2 is going to be 90 degrees. Right? So theta 2 is equal to 90 degrees. We have n1 sine theta is equal to n2 sine theta 2, which is, so we get n1 sine theta 1 is equal to n2 because sine 90 degrees is equal to 1. So we get sine theta 1 is equal to n2 over n1, so theta 1 is equal to arc sine of n2 over n1. If we do the critical angle computation for a particular example, so let's do it for air and water. So air is approximately 1, and water is 0.23. We get this computation, it's approximately 4.7 degrees. So that's saying if we're coming in over, so if theta 1 is greater than AC TIR, total reflection. And so if the angle is 50 or 60 or 70, that means it's coming in even more glancing. So, so this is a computation you can do to determine whether or not your refractive ray is even better. One more video on the details of ray tracing for this lecture. This one we're going to consider Fresnel equations. And here's the issue. So what we've determined is that if we have a sphere or a surface and we intersect that, okay, with our hit ray, that's not very helpful when that problem happens. So we'll try again. When we end up here with our ray at our hit point, some of the light is going to be from the reflected ray and some of it from the refracted ray. Okay. What proportion goes to each? And that's the question we want to answer now. So in this particular case, we have an Escher print, and we can see this, the fish under the water. We're looking down the fish so that mainly refracted rays are being effective, and we're not seeing too much reflection on the surface of the water. So here, we're seeing through the water. Up here, as the angle gets shallower, which we're in the water more glancing, less is being refracted, and more is being reflected. So as we change the angle in this particular thing, we're changing the ratio between the refracted and reflected ray. So I'm not going to expect you to derive the Fresnel equations in this class. I'm simply going to expect you to be able to use them. There's a couple variations. I'll be clear which one you're doing. In this class, in homework exams, you'll have access to equations like this, and it doesn't matter being able to use them or not. Memorize them so if you can understand them. So essentially, it's going to be the ratio F between reflected and refracted light. So we're going to go back to the we had before. We have the B and M for our surface points. We have the normal and the incoming V. And we have the indices of refraction. And so we're going to compute this little f term by the indices of refraction. Now, there's a variation in that term, which we see, which is this. If you go to Wikipedia, you will see this one by 0.0. equals n1 minus n2 divided by n1 plus n2 squared. And I invite you to see if these derive the same formula, but either way, these are approximations to complete, um, complete Fresnel equations. Schlick's approximations, these are the variations in it. So it gives a good enough result. You compute this based on the indices of refraction, and then we will punch them into this equation. We'll take the dot product. If these are normalized, that's a cosine. Then we'll determine how much, and this F is going to be the percentage reflected light. So this will be less than between 0 and 1. So if this is 50%, this is 50, means 50 is reflected and 50 is refracted. If this is 80%, it means 80 is reflected and 20% is refracted. So let's work for a minute with Schlick's approximation to get a sense for the equation. So I'm going to use a variation of the equation which looks like what's on Wikipedia, but using our F terms, plus 1 minus F times 1 minus cosine theta 1 to the 5th power. Okay, with F equal to n1 minus n2 over n1 plus n2 squared. Okay, so let's set up with n1 equal to 1 and n2 equal to 1.33, so we're going from air to water. Then we end up with the little f term equal to 1 minus 1.33 over 1 plus 1.33 squared, which happens to be 0.2. Small value. And if we start playing with some angles, put in 0 degrees, we end up with basically 0.02 plus 98 times 1 minus cosine of 0 degrees squared. But since that's 1 minus 1, this is equal to 1 minus 1 is equal to 0. We end up with, so most of the light is being refracted here. We're looking down into the surface. If we do 45 degrees, we end up with 0.2 plus 98 times 1 minus 707 approximately to the 5th power, which is equal to 2 plus 98 times 0.002. And so this is still very close to the same. Then if we get all the way up to 80 degrees, this ends up being closer to, okay, and this term ends up being close to 3.8. Okay, so we can see that we're starting to recover some of this, so we're getting to 40% of the light going into reflectance and the rest going down. And if we did f of 90 degrees, it'd be 0.02 plus 0.98 times 1 minus cosine of 90 degrees to the 5th power, but 90 degrees is 0, so this ends up being 0.02 plus 98 times 1 to the 5th power, which is equal to 1. And so at 90 degrees, everything reflects. You can see that the curve kind of starts out slow and goes up to 1 at the end. All right, so you'd use this in your ray tracer. You'd compute the Fresnel equation, and then you'd weight the component of the reflected and the refracted rays based on the result of this equation. I put in a blank slide just in case we need it, and that's the end.